Okay, so today we are going to discuss about extra session, live session. Overall, all the weekends up to week 11, we are going to cover up. So this is just a recap session, and we will be having followed by the um, content. We will be having question answer session. So starting from the basic fundamental slide, which shows three things coming out of the electromagnetic radiation. It is divided into three kind of modulation, fundamental modulation. One is amplitude, let me keep. Yeah, one is amplitude, another is phase, and another one more is wavelength based. Okay, so we have already covered up this amplitude, phase and wavelength modulation systems. Now the also we can say these are the pillar of the optical sensing. In the amplitude modulation, we play with the intensity. Intensity is nothing but the square of proportional to square of amplitude. So it's directly optical measurement can be done with a photo diode, and the application is trace gas spectroscopy, optical time domain refractometry, and what are the constraints? Highly susceptible to background losses and fiber attenuation. These are the constraints. Now moving towards the next modulation, which is phase or interferometry. So in this, the delay measurement via wave beating is done, and the application is fiber optic gyroscope. We have already discussed about this gyroscope, and then acoustic pipelines already have been discussed. Then what are the constraints? Extremely sensitive, but absolute phase is easily corrupted by environmental drift. Even a small perturbation can make a drastic failure in the measurement. Then moving towards the wavelength, which is very rugged. The most rugged is amplitude, but already it's having the background losses and fiber attenuation. That's why the intensity can also be survive up to few hundreds of kilometers. What about the wavelength then? Wavelength frequency shift or color shift tracking, spectral tracking. So the application are FBG, structural strain, all these things comes under this. And the constraint is the most robust architecture. Signal is encoded in frequency, rendering it immune to intensity fluctuations. So intensity doesn't matter here if you have low or high, but the wavelength shift itself is a very robust architecture signal processing thing. So one by one we'll move to from amplitude to wavelength modulation. The first one is amplitude modulation. There are two things: localized versus standoff detection. So these detections can be varying. So localized or standard. So we'll see. So laser and useful for the extracting intensity data, requires correlating optical power loss to physical space. So the first thing is the differential absorption localized, which we are going to discuss is localized, and then OTDR standoff. So in localized, what is happening? Tuning a laser strictly onto a molecular resonance, then slightly off resonance to bypass external system losses and isolate trace gas concentration. So you can see here that the laser, red laser with a P naught intensity is coming inside the chamber where molecules, gas molecules are there, and because of the absorption gases concentration, the absorption is happening because of Beer-Lambert law, can be calculated using the Beer-Lambert law, and the laser intensity, which is coming R, can be easily calculated. So this is one of the example of localized detection. What about the stand-up detection then? Stand-up detection is nothing but a OTDR. So remote sensing via relay scattering, spatial resolution is logged to pulse width, and a microsecond pulse at 1550 equals a 100 meter spatial window with a 52 decibel backscattering coefficient. So here is a OTDR. OTDR also we have discussed previously, where this is the equation for that. Moving towards the next thing, which is the receiver noise taxonomy. So need to discuss about what are the problem associated with the amplitude modulation. One of the thing is like noise, and in noise there are so many types of noise: short noise, thermal noise, Johnson's noise, and then current, dark current, and then amplifier noise. So mathematically also the density has been given, how we can calculate the noise, and what is the origin and mitigation also is mentioned here. For short noise, it caused by random Poisson distributed arrival of individual photons. This is fundamental physical limits and cannot be eliminated. So short noise is like a yeah, so it's like a random arrival of photon. It can be can't be 100% eliminated, but we can, if you use very coherent laser or something, we can allow the number of photons in per interval can be achieved of in a somewhat manner, but not fully, cannot be eliminated this noise. Then talking about the thermal noise, and it is already, you know, the temperature is proportional to the temperature. So random thermal motion of electron inside the TIA feedback register mitigated by cooling and altering TIA impedance. So yeah, obviously it is proportional to the temperature, so reducing the temperature can also reduce this thermal noise. And going towards the next thing, which is a dark current. It is also a thermally generated electron hole pair created in the absence of light, and mitigates via high quality semiconductor manufacturing and active cooling. Okay, semiconductor manufacturing and active cooling can be mitigated the dark current. Moving towards the next thing, which is amplifier noise. Amplifier noise has the inherent 1 by f and broadband op-amp density mitigated by the architecture, like a FET based op-amps like OPA 657 at 1.3 FA per under root hertz, square root hertz, drastically outperforms BJT based ones. Also, this amplifier noise can be resolved by using the number of um, accumulations by increasing number of accumulations. Here we are discussing about the quadrature lock-in detection now. Why? Because all these things we need to mitigate the noise, and we should get the clean digital signal. And to get that from noisy signal to digital signal, we need to have a proper lock-in detection. And for that, the baseband detection force system to integrate across overwhelming broadband noise. Lock-in detection isolates the signal via phase sensitive filtering, and you can see here phase sleeve multiplier. This is the signal. Then here local oscillator is there, mixing the signal and uh, propagating towards the signal to low pass filter, where it will clean overall um, noisy signal into clean DC signal is possible. Then we have already discussed about this quadrature tracking, this equation in the previous slides, where the quadrature tracking is nothing but the environmental noise has random phase. By splitting the reference into 90-degree shift shine and cosine channel, we isolate the exact signal vector and perfectly reject orthogonal noise regardless of phase drift. So this is also possible. Give me a moment. Yeah, so moving towards the next modulation type, which is a phase modulation, the where we are dealing with the interferometric converters. In a phase modulation, we have already discussed about how the phase is um, oscillating from pi to 2 pi. It's given an example uh, of phase delay versus the detection optical power. So how we can translate this phase into the actual signal carrier, um, um, how we can translate this one as a signal carrier. We can translate using the photodiodes, which are generally a fundamental phase blind, but we don't have any direct um, detector which can detect the phase. So for that, the photodiode, which are typically a phase blind, but it's uh, quite sensitive to the amplitude. So this interferometer converts the visible sub-wavelength phase shifts into massive intensity variations via the mutual coherence beating of reference and signal field. And using this, and using this, it can translate the phase into intensity and can used as a signal carrier. The sensitivity double edged sword, again the sensitivity. So this precision in the sensitivity we're talking about has an ambient pressure drop altering the refractive index. One of the reason is the pressure drop by just 10 to the power minus 6, and will completely destabilize absolute phase tracking, and that's why it's quite sensitive towards the ambient pressure change. Yeah, now moving towards the next thing, which is coherency. The coherence constant LC, uh, by Wernier-Khinchin theorem, the reach of any interferometric sensor is dictated by the temporal coherence of its source. So one of the example is given here: broad spectral width and short coherence length. We need to balance it out. For that, from few micron of the sensing application to few kilometers can be um, balanced it out using the different sources. One of the uh, short distance source can be in a short distance source in a short distance sensing, the source can be used as LED, which is having the high broadband, and del lambda is approximately full width half maxima is approximately 50 nanometer, and the LC is 20 micrometer. So its coherency is quite short range. Then moving towards the next thing, which is Fabry-Perot laser, which can be used up to 1 mm distance because of the coherency, and the full width half maxima is in a range of 1 nanometer, and the standard, it is used for the standard localized sensing. While we are dealing with the only the coherence length, then we can go up towards the FBZ lasers, which is this narrowband, and del nu is equal to 1 megahertz, LC few hundreds of meters, mandatory for long range pipeline acoustic sensing, which is a phase OTDR. Okay, now the next thing, managing polarization walk off. So the polarization we already have discussed about the phase thing, everything in the previous lectures. where we have discussed about the Fresnel-Arago law, which dictates that orthogonal polarization generates zero interference visibility cos 90, which is equal to 0. So once we have the orthogonal polarization, there will be visibility almost 0, and once it is moving towards the 0 0 parallel one, then there will be a degeneracy problem. Standard SMF has degenerate fundamental mode, odd and even, which are almost equal. Any microband causes unpredicted coupling, turning linear polarization into random elliptical drift. You can see here how the elliptical drift is happening. But if you are using the PM fiber, then this PM fiber embedded stress rods into the cladding. This physically breaks mode degeneracy via strain induced birefringence. Light launch on one axis cannot couple to other, and guaranteeing maximum fringe visibility. So that's why the PM fiber is a solution for this, managing the polarization. And then the phase synthesis for the interferometric fiber optic gyroscope, we have already discussed these things, where we need the navigational precision of 0.01 degree per hour utilizing the Sagnac effect, and the common path immunity is given here, which is because the CW and CCW counterclockwise waves travel the exact same physical fiber loop. All ambient temperature and pressure noise is perfectly reciprocal. They cancel each other out to 0, which is del phi. Del phi is equal to 0. Once the physical rotation breaks the reciprocity, the time delay differences generates a proportional phase shift, and because of that, del phi is no longer 0, it will be some value. This here mentioned ohm. This transform the setup into an ultra precise navigation tool, and that's why this is a very sensitive gyroscope which used in the aviation industry. Moving towards the next thing, which is coherent Rayleigh backscattering. So this, how we can defeating the coherent backscattering. The greatest threat is IFOG accuracy in CRB. Tiny density fluctuation acting as a random mirror. You can see here how much error is there. If you are using the simple SMF fiber, this much error is coming. But the problem is highly coherent laser allow backward scattering light from the entire loop to interfere with the signal, destroying phase accuracy. Now, using this error, which is lesser than 0.01 degree per hour, this can be used for the low coherency laser can be used to reduce drastically the error to less than 0.0 degree per hour, and which is very important to have to understand. And the solution is the low coherence paradox. By utilizing a broad source, LC is equal to 100 micrometer, scattering only interference occurs within exactly 100 microns of the receiver. Noise drops by 6 order of magnitude. So now we have finished off the phase modulated sensors. Now we are going for the wavelength modulation. For that, the best example is FBZ, and wavelength modulation permanently hardcodes sensor data into the frequency domain, making it impervious to background intensity loss. And either it is having very small intensity, low intensity, or very high intensity. It doesn't matter for this, but only the matters is the frequency domain where it is shifting, or what is for because of what it shifted. So you can see here that a transmitted beam from this side is propagating towards this side. Oh, sorry. Yeah. This is the input side. Okay, this is the transmitted beam. It's propagating, and here this is having the FBG grating. Once it is going towards this, one of the band from the broadband, one of the wavelength or frequency domain will reflected back because of this gratings, and the transmitted beam has the particular band missing from that, and it is mentioned here in this with this example of the spectrum, which input spectrum has clean broadband and the transmitted spectrum missing one wavelength, and reflected spectrum, which is the black peak, has a lambda b wavelength peak, which is usually shifts to another place because of the physically stretching or any kind of perturbation which is we are going to measure during the operation of FBG. Now we have discussed why it is happening, the reflected spectrum, why, how it is coming, but why this shifting is happening. So the dynamic FBG interrogation has a standard spectrometer, which are too slow to ultrascopic dynamic sensing greater than 100 kilohertz. We must convert wavelength shift back to intensity shift. So you know that already we have discussed about the wavelength shift here in this place, but still the wavelength shift cannot be directly used because of the its spectrometers are too slow to detect it. We need to change the CCD rotation very fast, and the second thing is it should be the accumulation time also requires quite high. And we yesterday we also discussed about the PGT, the piezoelectric effect also. It should be having the movement of in that range, but it's quite slow if you are doing this standard spectrometer for the wavelength shift to detect the wavelength shift. But if we discuss about the intensity shift instantly, it can be achieved. How we can achieve it? So we'll be having this static filter integrator grating, and here you can see that detected optical power and moving sensor lambda b. The matched interrogator, by routing the sensor reflection through a second static matched FBG, we exploit the linear slope of the transmission curve and instant optical conversion. As the sensor wavelength shifts across the integrator slope, the overlapping area changes. Wavelength variation instantly become readable amplitude variation. Linear range of 100 micron microstrain. Now what about the system synthesis? So um, for that system synthesis, the trace no gas sensor step 1 is source selection and differential detuning. The first thing is step 1, which is source selection and differential detuning. For that, you can see here the wavelength is 1100 nanometer and del shift is 73 picometer, which is minus 20 decibel drop, which is 100x, and this is because of uh, we are using here the DFB laser with a drive current of 35 milliamp. So what is the challenge here? The challenge is 10 hertz standoff sensor for nitric oxide, 0.5 amps gas cell, 1 milliwatt optical budget is the so this it's quite um, low frequency, and it's a very slow process to detect it, and the requirement is single longitudinal mode FBG laser, strictly narrower than the gas transition, which is 6 gigahertz width. Okay, so source selection and differential tuning we have discussed already. Differential tuning. Moving towards the next thing, which is a trans impedance amplifier, TIA. For that, indium gallium arsenide photodiode can be which is attached with the TIA with a feedback resistance, and for this the receiver sizing silicon crashes at 1100 nanometer. Select indium gallium arsenide photo PIN diode, which is having 0.7 amps per watt with 90% background loss. Baseline is 0.1 milliwatt. RF size to 14.3 kilo ohm to exactly fill the 1 volt of ADC. So now the noise reality, we'll discuss about this one. High optical baseline pushes the system into the short noise limitation regime. However, low 10 Hz sampling exposes the baseband to op-amp 1 by F flicker noise. One is the thermal noise, amplifier noise, and the short noise. So these are the things we need to take care of. Then the step 3, which is signal extraction. Here this 1 by F flicker noise should be eliminated by the lock-in detection 2F, increasing the frequency and bypassing the short noise floor. Baseband detection limits sensitivity. Apply wavelength modulation spectroscopy WMS at 10 kHz. Lock-in detection moves the signal entirely out of 1 by F regime for zero background extraction. Concluding, this is the conclusion. The ultimate limit of optical sensing is never the signal, it is always a noise. Mastery over optics is the mastery of selecting the right modulation paradigm to outmaneuver environmental chaos. So these are the things we need to take care: source selection, receiver sizing, and then signal extraction. And in the end, the optical sensing is limitation is not the signal can be detected even with a trace amount of uh, information, but the ultimate thing is the noise, which is ruining overall detection system. Okay, so where here we'll stop. We have already discussed about amplitude modulation, phase modulation, and wavelength modulation sensors. Now we'll take 5 minutes break. If you have any doubts, Sunny, you can ask me or anyone, and after that we'll start from this question answer sessions. We have almost 10 questions, and okay, so give me 5 minutes break. Okay, let's start the question answer session now. Jenny, you have any doubts till now? If not, I can move towards the question answer. Okay. So first question is, in an OTDR system, the spatial extent of the pulse W is defined as W is equal to Vg tau p by 2. Why is the factor of 2 included in this spatial sampling calculation? What is the requirement of 2 here? Option A, it is a correction factor for the exponential attenuation e to the power minus 2 alpha L seen in the power truss. B, it compensates for the group velocity being half the speed of light in the vacuum. C, it represents the newest sampling limit for the pulse width duration. And D, it accounts for the pulse traveling to the scattering point and returning to the receiver.
Option D.
Option B. Fourth option or second option?
D, sir.
Okay.
Option 4.
Option 4, yeah. It accounts the pulse traveling to scattering point and returning to the receiver. Yeah, you are correct. So back the signal is moving, returning to the receiver, and that's why it is taking time. So option D is correct. Let's check. Okay, that's right. You're doing good actually. Next question. In the context of noise is an optical receiver, why is a FET based op amp like the OPA 657 often preferred over a BJT based op amp for the front end trans impedance amplifier TIA? A, FET based op amps are immune to 1 by F flicker noise at low frequencies. B, FET based op amps exhibit significantly lower input noise current density. C, FETs eliminate the need for the feedback resistor RF, reducing thermal noise. D, FET based op amps have much higher gain bandwidth products. What's your answer for this?
Option B, sir. B.
Okay. So FET based op amp exhibits significantly lower input noise current density. That is correct. That's why we are using FET, not BJT based op amps. Moving towards the next question. An interferometric fiber optic gyroscope utilizes a phase bias to operate at the quadrature point. What is the preliminary reason the bias must be time varying or non-reciprocal? Option A, in a common path Sagnac loop, a static phase shift is seen equally by both beams and cancels out. B. The time varying bias is required to compensate for the Earth's magnetic field rotation. C. Static phase bias elements introduce excessive shift effect noise, and D. A static bias would prevent the detection of the sagnetic phase shift del phi s. What's your answer for this? Janvi?
Yes, sir, I'll take little time.
Hmm? What happened?
No, sir. To find the answer.
Difficult, huh? Why we need the quadrature point? Here the correct answer is option A. Why is it so? Because we have already discussed that reciprocal phase shift affects the clockwise and anti-clockwise and clockwise um, it should be identical at the quadrature point, and necessitating a time varying modulation to create relative phase differences. So that's why this is the equally by both beams and cancels out. Moving towards the next thing, which is when designing a wavelength modulated sensor using a fiber Bragg grating, what is the matched filter interrogation technique? Option A, selecting a laser source whose line width exactly matches the full width half maximum of FBG. Option B, applying a digital Kalman filter to match the predicted strain with the observed Bragg wavelength. And option C, matching the indents to the photo detector to the output of the FBG to maximize power transfer. And the last option is using a second FBG with an identical spectrum to convert wavelength shift into intensity change.
Option D, sir.
Option D, using second FBG with an identical spectrum to convert wavelength shift into intensity changes. Yeah, it's correct. Okay. Next question, in the detection, why is quadrature detection measuring both Vx and Vy superior to a single channel phase sensitive detector? Option A, it eliminates the need for a low pass filter LFP at the mixture output. B, it allows the system to detect signals at twice the modulation frequency. C, it doubles the signal to noise ratio by sampling the noise twice. D, it allows the calculation of the signal magnitude independent of the phase difference between the signal and reference. Any answer?
Option B.
Option B or D?
D, sir.
Second option.
Fourth.
Fourth. Yeah. So you are correct. Why is it so? It allows the calculation of the signal magnitude independent of the phase difference between the signal and reference. And it is because by taking Vx square plus Vy square in under root, the amplitude can be retrieved even if the signal phase drift or is unknown relative to the local oscillator. Okay. Next question, which is, for a phase modulated sensor to operate over a 10 km distance, the source must have a high coherence length. What is the approximate required spectral width del nu for such a system? In order of 1 kilohertz, in order of 1 gigahertz, in order of 1 terahertz, and the spectral width is irrelevant of the coherence receiver is used. Which is the correct answer here?
One kilohertz.
Why is it so? How we can calculate this, LC? LC is given here, approximately operates over 1 kilohertz, 10 kilometer. Okay, 10 kilometer in the sense this coherence length is nothing but a C by del nu. C we know, this also we know, greater than 10 kilometer. So if you calculate del nu, it will come extremely narrow, typically in kilohertz region. That's why in order of kilohertz region we can use. The spectral width will be in kilohertz region. You are correct. Okay, moving towards the next question. In the analysis of the fiber optic, no, this is not this one. Yeah, the axis noise factor FA in an avalanche photodiode is primarily a result of what physical phenomena? Option A, random nature of the impact ionization process during implication. B, the use of high K dielectric to reduce leakage current. C. The mismatch between the refractive indices of the P and N layers. D. Thermal generation of electron hole pairs in the deflection region.
Option A, sir.
Option A. Yeah. In avalanche photoreal, we need to think about this one. What is the physical phenomenon? The random nature of the impact ionization process during the multiplication. Okay, so this excess noise factor is result of this random nature of impact ionization. Okay, nice. You are doing good. Second last question. In a phase OTDR distributed acoustic sensor, how are acoustic perturbations localized along the fiber? A. By shifting the laser's frequency until a resonance is found at the leak location. B. By placing discrete FBGs at 1 meter intervals along the pipeline. C. By measuring the time of flight of backscattered light from the coherent pulse. And D. By using a 3-axis gyroscope to determine the physical displacement of fiber.
Option B.
Option B.
Discrete FBGs.
B or D? Okay, this one. Okay, okay. But there is no by placing this along the pipeline. No, this is not the correct one. Why is it? Because FBG provides point sensing, and phase OTDR is distributed technique using a fiber's intrinsic Rayleigh scattering. So this is not the correct answer here. We need the correct answer, which is option C. By measuring the time of flight of backscatter light from a coherent pulses. Here we are discussing about the phase one, phase OTDR. Like standard OTDR, the distance is mapped to the time of delay of the return signal. But here in phase OTDR, looks at phase variation between successive pulses.
Okay, sir.
Okay, moving towards the next question. Did you understood? This is a phase OTDR, so we need to have to measure the time of light of backscatter light from a coherent pulses.
Wavelength only FBGs. Okay, sir.
Moving towards the next question, what is the Faraday effect in a fiber optic gyroscope and why is it problematic? Hmm? It is a non-reciprocal polarization rotation caused by external magnetic fields leading to phase errors. B. It is the loss of light due to macro bending in the fiber spool. C. It is thermal expansion of fiber spool which changes the loop area. D. It is the interference between the cladding modes and the core modes. Tell me your answer.
Option A.
It is a non-reciprocal polarization rotation caused by external magnetic field lending to pressure. No, it's not correct. In this case, you are telling about the what is that? Yeah. So because the Faraday effect. Okay. Yeah. You are correct. It's a non-reciprocal, not reciprocal. So because the Faraday effect is non-reciprocal and the phase shift does not cancel the counterclockwise and clockwise beam, creating a false rotation signal, and that's why it is a problematic. So polarization rotation caused by external magnetic field leading the phase errors, and that's why this Faraday effects is problematic here. Okay, so yeah, you are correct. Yeah, I just misunderstood the reciprocal and non-reciprocal. Okay, then here we are going to finish our today's session. If you have any doubts, you can ask me. Are you are, are you doing properly all the this weekly assignments?
Yes, sir.
Yeah. Okay.
Sir, lock-in detection. The amplitude analysis.
Lock-in detection. No? Yeah. Here you are talking about.
Yes, sir.
What do you want? Uh, do you want to explain me?
Uh, Need for quadrature locking detection. Normal from normal locking detection. What
Uh,
is quadrature locking?
Here it is mentioned that this is it. It takes the quadrature means it takes the 90-degree shift of sine and cosine channels. Both it takes. That's why it is a quadrature. I'll tell you. Wait. Um, Noise. So what is happening in this? The quadrature noise lock-in detection. Why we need? Because in the quadrature, the first thing is our signal sometimes is buried inside noise. Suppose you have the noise like this, and you might be having one small signal here somewhere, like this. Okay, this part, and you want to detect it. So what you can do, what you need to do is you need to use the quadrature lock-in detection, which is a technique used by extract a very weak signal buried in noise. So in this noisy signal, you might be having one clean DC signal, and you will be having one small signal like this, or it can be a Gaussian also, like this. Okay, I'll just keep a line. So we need to detect this one. So how we can do it? By comparing it with the known reference signal. And how we can compare it? Instead of just measuring amplitude, it measures both amplitude and phase. Okay. And how it does is both amplitude and phase using two components. Which are the two components? One is the in phase x aligned with the reference signal, okay, and another one is quadrature, which is a 90-degree phase shifted from references. You can see here, this is your real part and this is your imaginary part. So you are detecting phase in phase aligned with the reference signal, along with you are also detecting this 90-degree phase shift from the reference. So it can be in the middle also, and can be also at 90-degree here, or it can be at the 30-degree, 20-degree, those things. So here uh, the phase shift will be the amplitude. First of all, amplitude will be responsivity is v x square plus v y square, and the theta, or theta means the phase, will be tan inverse v y upon v x. This one what is written here, the shift, or you can say del t, del phi or del theta also. So that's why we are using two things. One is for the phase, another for um, the amplitude. Understood? So this one is giving, this part is giving x, which is cosine component, and this part is giving us the sine component, okay, y. So we need to check this one. Lock-in detection means this part somewhere here. Are you understanding, or it's difficult to understand? Should I explain more in detail? Yeah.
Yes, sir.
Just a second, I'll explain you little bit more. So how it works is, I'll explain here, okay? If you understand, let me know. Suppose you have a signal like this something, okay? This is your noisy signal. You can't even distinguish what is coming here. You might be having this part one peak, this part one peak. It's like a phase you are getting, okay, little bit, but still you can't say that whether it's a noise or it's a signal. So this is from the you are seeing this part, we can see as an amplitude, this gap, and you need to see this part, from this part to this part will be a phase, okay, and phase will be this much. Now quadrature means you are taking the lock-in amplifier, you are feeding it to lock-in amplifier, and from there it is going to the amplitude r and phase theta. Amplitude you have, which is r, and phase you have theta. Now just a second. So you will see from here to here, you might be having the signal. This is one axis, this is another axis, and here it is, you are having 0. So the quadrature component is like just second. Yeah, so you have a quadrature component. Suppose sine will be like this, suppose. Okay, so increasing, and in this place, particular place, change the color. Let's see how it is coming. Pointer, this case I am taking, and you have cosine will be like this. Okay, so not like this, like this, something. It's a decreasing, diminishing. So one thing is there, that cosine will go like this. If you are uh, taking the example of that cosine theta cos phi t time dependent phi, so it will be like this, and for the sine it will be opposite. It will be like this. Okay, and which will be sine phi t, and that's why we need these two, sine and cosine both here, and this particular place it is matching. Okay, so it's like the intercepting point here. But if you see, I need to little bit shift it so you can understand here. If you see here, no, green I want, green, yeah, this one. Suppose if you see here like this, okay, so you can see here that both the component of the cos and sine, which is a quadrature component, making sure that both are mixing well and having the the face with merging together. Suppose here you can understand, color, let's take blue color. Yeah, so now you can see the loss of, because of the sine and cos, can be compensated because of both the amplitude and the phase. Like this, you can see here, sine part is enhancing like this, amplitude is increasing like this, and cos part is decreasing. But if we overlap both and see the amplitude, and because of the phase matching, the amplitude will be having the almost constant linear manner, with a temporal with a time dependent. So this is a time t, and here is the amplitude. So you can see that if you have two components, which are the cos and sine, and has the intensity is varying during the during that. So first thing what is happening, the phase, both phase are matching. Wherever it is matching, it is having the maxima, this part suppose. Okay, and also the amplitude is maximum, even though the amplitude of the sine is very small here, low, but the overall amplitude is high. Understood what I'm saying? That's why we need the lock-in amplifier, which is quadrature based. So that's why it can be, we need to calculate here, everywhere. Wherever the maximum is coming, that one we need to take, we need to consider it. Are you understanding what I'm saying?
Okay.
If you don't understand, you can ask me again. I'll discuss next class again, this noise one.
Okay.
Hmm. Okay, do we have any other questions?
No, sir. No, sir. Go through what?
Uh-huh. You have any question?
No, sir.
Okay. Hmm.
Sir, regarding the question paper,
Uh-huh.
toughness level will be related to
What?
assignment questions or
Yeah, assignment.
pre-solved some questions. Sir,
No, it will be the similar to the assignment question only. It won't be that much hard, it won't be that much easy also. But whatever you have solved in assignment, that much hard it will come. That much the level of the final question also.
okay, sir. Is there any possibility to get the previous year question papers at all?
Is there any
The
previous year?
previous year
Previous year.
question.
Uh, I will convey the message to the instructor, course instructor. He may uh, tell something. After that, I'll tell you, because directly I don't have any access to the previous year question paper.
Okay.
Mm-hmm. So you are from VIT Vellore.
Yes, sir.
Okay. I'll convey the message to him. Let's see how what he's saying. Okay. There is one more example. If you can, in just a second, I'll tell you. Uh, Okay, then if you don't have any other questions, I can just close the live session today.
Okay, sir.
Yeah, we'll be having a meeting on 9th Thursday. That will be the last live session. At that time, I'll tell you what supervisor is saying, instructor is saying about the question, previous year question. If you want, I can ask him.
Okay, sir.
Yeah, and if you have any doubts, also you can directly convey the message to him.
Yes, sir.
Okay then. Thank you for joining.